Let's discuss integrals involving trigonometric functions, everybody's favorite. Now, in this section and in the next one, we will be working with trigonometric integrals, whether they involve trigonometric functions or we can substitute something for them to involve trigonometric functions. And therefore, these two sections will require familiarity with trigonometric functions, more specifically sine and cosine, several identities, and general comfort level of dealing and simplifying with those. If you need to review trigonometric functions at this point, please do check out the pre-calculus refresher modules that are posted on our Blackboard page. There's a section devoted to trigonometric functions. Now would be a good time to review it. So let's take a look at this first one here. I have sine x times cosine squared x. This is one of the integrals that we likely have seen before or something similar to it. You notice that both sine and cosine are present here, and therefore there is hope that a simple substitution will work. In fact, we notice that if we substitute u is equal to cosine x, dx and sine x will actually form du. So this is quite convenient, and therefore this integral can be in fact solved using a simple substitution. Yes, it's a substitution that involves a trigonometric function, but as the actual integration technique, it is only a substitution. So the derivative of cosine x is minus sine x dx, and therefore what do we get altogether? This will give me u squared, sine x dx will give me minus du. Be careful about your signs here. So my integral in the next step, rewritten fully in terms of u, will be minus u squared du. Now, of course, I can integrate this fairly quickly, u cubed over 3 plus a constant, and then I can simply return to my original variable by plugging in the fact that u is equal to cosine x. So therefore, whoops, lost minus here. My final answer is going to be negative cosine cubed x divided by 3 plus a constant. As always, remember that you can differentiate the final answer to check whether or not you've performed the integration correctly. If you have, then what you should get back is what's inside the integral here. This is not going to take too long to see that indeed you are going to get what you need. Now, this was fairly simple, but notice that all I needed in the substitution was cosine, and that resulted in this extra factor of sine that was present in the integral and therefore aided the substitution to be carried out. The one thing that didn't actually matter whatsoever was the power on top of the cosine. So if this is my first example, let's take a look at the next one. What if the power was, let's say, 30? Cosine to power 30 of x dx. Would my approach to solving this integral change in any way? Not really, because notice that again, if I set u to be cosine x here, then du, as before, will simply be minus sine x dx, and then the rest of the calculations will look analogous to before. This will be u to power 30, and sine x dx will together form a negative du. So what is important here is the fact that both sine and cosine are present, therefore setting u to be cosine produces this extra bit of the sine x that does appear in the integral and therefore can be in fact combined into the du, but what really doesn't change the entire method of evaluating this integral is the power itself. Also notice that this would be very similar if my example had sine and cosine roles switched in this integral. If I, for example, had sine to power 30x times cosine x dx, this integral we would be able to approach in a very similar fashion. My substitution here would have to be for sine x to be u, and then du would actually be the entirety of the rest of the integral. So if I have one of these trigonometric functions appearing by itself and another one appearing to any power whatsoever, then the integral can be solved by a simple substitution because of how sine and cosine relate to each other via differentiation. Let's take a look at the integral that doesn't have one of each, but has only one of the trigonometric functions to some power. So here I have sine cubed of x. What we noticed in the previous example is that it is very beneficial to have both sine and cosine present, because then if I sub in for one of them, the other one will appear as a u. So one thing I can do here is rewrite sine cubed x as sine squared x times sine x, and then don't forget our dx. Now I'm doing that so that I can get sine squared x. Remember, the basic trigonometric identity states that sine squared of any angle plus cosine squared of the same angle is equal to 1, which means that I can take this sine squared and rewrite it in terms of cosine squared. So as my next step, I can have, instead of sine squared, 1 minus cosine squared x sine x. And then I can simply open up these brackets here to obtain integrals that are something that I can actually anti-differentiate. So the first one is going to be sine x, and the second one is going to be minus cosine squared x sine x all times dx. Right? So notice that all I did was open up the brackets here. Now I can, of course, integrate one at a time. Integral of sine x, I already know. This is a very straightforward integral to figure out. And the integral of cosine squared x sine x is exactly of the type that we've seen on the previous slide, where one of the trigonometric functions, sine and cosine, is present to degree 1, and the other one is present to some other degree. So this portion I can apply a substitution to and figure out how to do. So from here on, I'm going to leave the rest of the computations to you as extra practice. Make sure you can actually finish this off. Now, this is what we'll have if I have sine cubed x. What if I had something else? What if I had, for example, sine to the power of 33x dx? Would I be able to carry through a similar approach? Well, all I've done here is separated sine squared in order to rewrite it in terms of cosine. And then once I had that, the second piece served as my eventual substitutions derivative. So if I have sine to power 33x, then I can do something very similar, where I will separate one of the sines in order to get at that substitution sine x dx, and the other sine that now appears to an even power, I can leverage my basic trigonometric identity towards and rewrite all of this in terms of cosine. Now this integral is going to be a little more finicky because the power is bigger, so you're going to introduce this term to some other power and therefore might have to consider other options, but it is actually solvable by a similar technique. So the idea here is if I have sine or cosine to an odd power, then I can split one of them away, which will result in the function being left to the even power, at which point I can use the basic trigonometric identity to bring in the other trigonometric function to apply the substitution for. The moral of the story here is that odd powers are good. These integrals can be generalized, and this approach can be generalized to any odd power for either sine or cosine. In fact, I should point out that we will mostly deal with integrals that will involve sine and cosine. We will once in a while see integrals with tangent and secant as being with a similar relationship as sine and cosine, but most of the integrals we'll consider will involve sine and cosine as our basic trigonometric functions. So odd powers are good. Now, why are even powers not so good? Well, the idea here is that if I take an odd power, I can split away one of them in order to produce this term that will eventually become my du. If I have an even power to begin with, splitting one sign, let's say, away will not result in anything useful. So what do we do with even powers? So again, notice that of course here I can rewrite this as sine x times sine x dx, but then I run into a problem. If I substitute sine x for u, then my du will be cosine x dx. But what I have remaining is sine x dx. And because this is not to an even power itself, using the basic trigonometric identity is going to be really quite ugly, because the basic trigonometric identity only involves even powers. Solving for sine here will introduce a square root, and an integral of a square root is not something that we would ever really like to deal with if cannot be avoided. So here, let's think about what other things I can apply other than a straight substitution or the splitting away of one of the factors. One other thing that I can apply, and the thing that we will always apply with integrals that involve even powers and even powers only, notice that there's nothing else here, are half-angle identities. Now, luckily, you are all in front of computers and have your notes with you, so you need not memorize these formulas, nor would I ever have made you even in face-to-face class. This is something useful, though, to have on hand with you when solving integrals involving trigonometric functions. The half-angle identities tell us how to rewrite an even power in terms of double the angle. So sometimes they're called double angle identities, but most of the time they're called half-angle identities because this angle is half of the one that is being rewritten in terms of. Here I have an integral of sine squared. So instead of sine squared, I will actually use this first identity and reduce the power of 2 down to simply cosine of double of the angle. So the main benefit of using these identities here is in fact to reduce the power of the function that I am using. Now, once I'm down here, it all comes down to simply rewriting everything and thinking about how I can integrate the remaining portions. I noticed that here, there's really not much left to do. Once we open up the brackets and distribute everything in, I am down to 2 integrals that can be anti-differentiated fairly quickly. So this integral here, integral of simply 1 dx, is going to be x. And this second integral here, you can do the substitution for 2x here in order to make sure that you got the right coefficient going out. Or if you've already practiced substitution enough, you might just be able to tell that the antiderivative here will be sine of 2x divided by 2, plus of course a constant. Once again, we can take a derivative of this in order to make sure that what we get back is our inside of our original integral, and therefore that our integration was performed correctly. Now, this is if you have only one trigonometric function to the even power. What if you have more than one? What if we have sine squared times cosine squared? Remember the very first method we talked about? What if I simply let u be equal to one of these functions? They have the same power, so it's kind of all going to be the same. What if I let u be equal to sine of x? Then my du is cosine x dx. And I noticed that I kind of ran into the trouble again right away, because this term will become u squared. Cosine x dx will become my du, so one of the cosines will be taken up by du, But then I'll be left with one single cosine here. Again, basic trigonometric identity is mostly used for, or nicely used, in the cases when the degrees are even, and I will no longer have an even degree on the cosine. So this method is not ideal. This integral, though, can be approached in a variety of other methods. Let's just consider a few options that we've already seen. So the substitution didn't work. What about rewriting one of these in terms of the other function using the basic trigonometric identity? So what I can do, as let's say my first method, is to simply rewrite, let's say, sine squared as 1 minus cosine squared x, and then I'm going to have cosine squared x remaining, right? So I just replaced this sine squared with 1 minus cosine squared. Then let's think a few steps ahead. We're kind of like chess masters now, thinking whether or not it's going to work out without actually necessarily working it out. If I open up the brackets here, what I'm going to have is, well, let me write the next step. I'm going to have cosine squared x minus cosine to the fourth x dx. So what I'm going to end up with are two integrals, each of even power, but containing only one of the trigonometric functions. Each of these integrals can actually be solved using the method on the previous slide. All we're going to have to apply are half-angle identities. Now, you might have to actually apply them here more than once because the power on this cosine is not just 2 but rather 4. So you will have to take the half-angle identity for cosine squared and then square it again. So this is going to take some time to work out, but it will actually work. What else can we do here? Well, the other thing we can do is actually apply the two double or half-angle identities right away, right? So let's just recall what they are here really quick. I'm going to put my two formulas in the bottom here, so I'm reminded of how to use them. So here, I can simply replace sine squared with its expression in terms of the double angle and cosine squared with its expression for the double angle. So I'm going to have 1 minus cosine 2x all over 2 times 1 plus cosine 2x all over 2. Then, what are we going to do? Well, I'm going to take out these two 2's to the outside of the integral, and then on top, what is my next step here? Let's write simply the next step just to be sure that we are actually on the way to producing a solution. If I FOIL these two factors out, or if I simply remember the difference of squares formula, then what I can see I can get here is 1 minus cosine squared of 2x dx. Now, what would I be doing at this step? I would be splitting up this integral. The first part I can take an integral of. What about the second part? How would I integrate cosine squared of something? Well, cosine squared of something is an even power, and as discussed on the previous slide, and is similar to this integral here, I would be simply using the half-angle formulas again. So yes, now my angle is 2x, so when I plug it here, my result on the right-hand side would be double that, so 4x, but this is still simply involving the half-angle identities. The third way that I will suggest here, and it is by no means the only other way, is the way to actually leverage other types of trigonometric identities. So if you've had a lot of practice with trig identities in high school, you might recognize this insight as something that is familiar. And it is in fact a double angle identity. I know that sine of 2x is actually 2 sine x cos x. This is the other useful identity to know. And then what I notice here is that if I square both of these sides, I will in fact have sine squared cosine squared, which is what I have inside my integral here, except for with the factor of 4 in the front. Now, if I simply divide everything by 4 now, I can use the left-hand side here. So what I'm going to have for my third way is to notice that this entire integral is actually 1/4 of sine squared of 2x. Once I'm down to here, I am in a similar situation to this case, where I notice that I only have an even power, and therefore I can apply half-angle identities, except for I have to be careful that I will be doubling the angle that I have, resulting in the 4x on the other side. So in this case, this is how it's going to work out, but I'm once again going to then apply the half-angle identity. Let me write out just the next step for example, this guy, to make sure that we can plug an angle that is not simply x into a half-angle identity and produce the correct expression. So if I apply the half-angle identity to this sine squared here, what am I going to get? This integral is going to be 1/4. This 1/4 just comes from here. And then sine squared of 2x. So my angle now here is 2x. My formula says to take what I have and double it, which means that within the formula, what I should see on the right-hand side is now 1 minus cosine 4x over 2. So 1 minus cosine of 4x over 2 dx. And then this integral now is actually going to be very straightforward to take an antiderivative of, because I notice that once I get rid of all of the constants, I will be simply integrating 1, which is x, and then integrating cosine of 4x, which is going to be sine 4x over 4. So the idea is, while we can solve integrals involving even powers are clumsier. Even powers make us go through half-angle and double-angle identities, and while they're not difficult, they will involve quite a bit more algebraic manipulations. I recommend that you go through the first two and maybe the third calculations to the end, just to make sure that you can actually carry them out procedurally. Now, the next thing we're going to talk about is what I call not obviously trigonometric integrals. So let's take a look at these two. I have the integral of square root of 1 minus x squared, or an integral of a square root of 1 plus x squared. Well, they don't have any trigonometric functions in them, so why would we be covering them in this particular section? Well, that's because let's just take a look at this first integral. How would we approach it in the first place? There's nothing I can substitute for, because what I would really like to substitute for is the inside of a square root. But if this is my u, then my du is going to be minus 2x dx. And I don't have this extra factor of x anywhere in this integral, which means that the substitution will not work. Well, what else is there to try? There is nothing that will help me break apart this integral at all, so my other attempts at simplifying are stopped before they can even begin. One thing to remember here, though, is that 1 minus something squared is an identity we've already seen earlier today. In fact, let's recall not one, but two basic trigonometric identities. They come from the same idea, but can be written differently. I have that sine squared x plus cosine squared x is equal to 1, which can then be solved for either sine squared or cosine squared. Let's say here I can solve for cosine squared, and I will get 1 minus sine squared x. And this is kind of like the form of what we have under the square root here. The square root will in fact make it even simpler, because if I square root both sides here, I notice that on the left-hand side, I can cancel out the square root and the square to produce cosine alone. So the even powers here really help us to simplify the square root. My second basic trigonometric identity can be derived from the first one by simply dividing everything by cosine squared x. What am I going to obtain? Sine squared x over cosine squared x is tangent squared x. cosine squared over cosine squared is simply 1, and 1 over cosine squared is secant. So this is how we get to our second basic trigonometric identity, the fact that tangent squared x plus 1 is equal to secant squared x. I'm going to rewrite this in the most sort of useless form, but just to be consistent with the previous line, I'm simply going to swap left and right sides here. So secant squared x is equal to, well, let me swap the signs or the constants too, just to align everything to what I have above, 1 plus tangent squared x. And now let's see, this 1 plus something squared is in the same form as this, 1 plus tangent squared. And again, taking the square root is not even going to be detrimental here, because if we replace the right-hand side with the left-hand side here, the square root and the square simply gets cancelled, producing a reasonable expression of simply secant x. So then, let's think, for example, about taking this one integral and how would that look if I am to replace 1 minus x squared with 1 minus sine squared. First of all, our very first consideration has to be the fact that I need to be mindful of the domain. What I have here currently is that the inside, what happens under the square root, has to be positive, because otherwise I simply cannot take the square root of that number. Am I guaranteed that by performing this substitution, what I get is going to be positive? Well, this is the one nice thing about trigonometric functions, is that they are bounded between -1 and 1. So the smallest sign can be is -1, and then all the way through 0 to the biggest it can be is +1. So this expression, no matter what the sign value is, will in fact always remain positive, which works out just perfectly fine for my domain. So if I can perform this substitution and replace the inside of my square root with this trigonometric expression, I will be safe in terms of where my function is defined. What we're going to look at next time is how to actually perform the substitution and how to then evaluate the resulting integral.